In this next video, we'll cover weak learners, otherwise known as decision stumps. A weak learner is defined to be a classifier that is only slightly correlated with the true classification. That means it can label examples only slightly better than random guessing. For example, it might be a simple threshold on a single feature. Or it could be a linear or even non-linear classifier. However, in the context of ensemble learning, which we will cover next week, it generally means a simple learning rule applied to a subset of the feature space. The idea is that each individual learner performs only slightly better than chance, but when many weak learners are combined together, they can be more powerful. In what follows, for the rest of these video lectures and the tutorial, we will stick with an axis-aligned classifier. The idea here is that for all the examples in the data, you're given just one feature, and you need to decide on some threshold on that feature that will give the best separation of the examples. Or if we were talking about regression, then the best fit of the data to the dependent variable. For this toy example here, we see our features are linearly increasing, and hopefully you can see that there is a clear pattern that separates the two classes. Can you suggest what a sensible threshold would be to separate the classes based on this feature? Stop the video and answer the question in Keats. So this type of weak learner is also known as a decision stump, which at the same time can be seen as a tree with one internal node. Here we refer to the input node as the root and the terminal nodes as the leaf nodes. The idea is that data comes into the root node, a feature is chosen to threshold on, an optimal threshold is then found, and then data less than the threshold takes the left path, and data greater than the threshold takes the right path. So you can see for this diabetes example that the feature chosen to split on is blood glucose. The learning rule then returns a threshold of 12, and all examples with values for that feature of less than the threshold go down the left path, and all examples for values of blood glucose greater than 12 go down the right path. The terminology of the root and leaf nodes refer to the very first node and the very last node of any tree, and therefore more generally we refer to the parent node with the leaves each as a child node. Please remember this terminology, as in the next video it will allow us to stack these decision stumps together in a tree. In this lecture we will consider two different learning rules, where in these lectures we will specifically look at classification rules in detail. So these rules do not apply for regression. We will briefly look at a regression rule at the end of this lecture, but it is just the classification rules that you will be expected to calculate by hand. The two rules we will look at are first, information gain. This compares the entropy of the mixture at the root or parent node, J, with the combined entropy of each of the leaf or child nodes, I. Entropy measures disorder, so we want to decrease entropy so as to generate leaf nodes which have better separation of class than the root node. So in this equation, H refers to entropy, where H of Sj is the entropy of the parent node, and H of Sji is the entropy for each leaf or child node. Here, the magnitude of Sj is the total number of data points reaching the parent node, and the magnitude of Sji is the total number of points reaching each child I from the parent J. And these two values are used to create a weighted average of entropies of the children. Second, we will look at Gini index, which similarly looks at how mixed the classes are after a split, but instead of using entropy, it just looks at the relative proportion of each class in each child node. So let's go into this in more detail, starting first with information gain, which requires a formal definition of entropy. We calculate entropy from the proportion of elements in each class, P/K. Look at these examples of mixtures in the purple circles here. The first example is very mixed with even numbers of crosses and circles. Here, each of these represent a different class. So the crosses represent label 1 and the circles represent label 2. The second example is less evenly mixed with only 2 circles and 7 crosses. In the last example, we only have crosses. So if we estimate the proportions of each class within each circle, for the first example, we have 10 examples in total, 5 crosses and 5 circles. So the proportion is 5 out of 10 for both, in other words, a half. In the second example, we have 7 out of 9 crosses and 2 out of 9 circles. So P of Y1 is 7 out of 9 and P of Y2 is 2 out of 9. Finally, for the final example, you can see that we have a complete separated mixture. So we have 0 for class 2 and 7 out of 7 are from class 1, so the probability of Y1 here is 1. We next calculate our entropies using this formula. So in the first case, since both the probability of Y1 and Y2 are half, the bit within the sum here is 1/2 times log to the base 2 of a half, which because they're both the same, we can multiply that by 2. So this gives us an entropy of 1, which is the maximum possible entropy. In the second case, we need to write out the sum in full. So for class 1, we have 7/9 times log of base 2 times 7/9. And for the second class, we have 2/9 times log of base 2 of 2/9, which gives us a total of 0.7642. Finally, for the last example, as the probability of Y2 is 0, we don't need to calculate that component of the sum. And so the entropy is just given by -1 times log to the base 2 of 1, which is of course 0, since log of 1 in any base is 0. So this therefore returns the minimum entropy of 0. So in summary, the more mixed up, the more disordered the mixture, the higher the entropy. Finally, to maximise information gain, we need to maximise the difference in entropy between the parent node and the weighted sum of entropies from the children. By doing so, we learn more about our dataset and gain more information on how to separate it. So here, the weighting in this sum is determined from the proportion of examples that reach each child from the parent. Let's go through a worked example. So in this example, for the parent, there are 23 instances or examples, 14 circles and 9 crosses. In the left child, child 1, there are 12 instances with 10 circles and 2 crosses. And in the right child, there are 11 examples with 4 circles and 7 crosses. So the first thing we need to do is estimate the entropy for the parent in each of the child nodes. So let's start with the parent node. And from the proportion from each class, we get 14 out of 23 circles and 9 out of 23 crosses. So if we plug that into the formula for entropy, which is up here, we have this part for the circle class, this part for the cross class. So we combine those together, making sure that we remember the minus sign at the beginning. And this gives us an entropy of 0.966. So it's very mixed. For the left node, the proportions are 10 out of 12 and 2 out of 12, so it's much less mixed. And when we put all this together, we get a reduced entropy of 0.65. The right node remains quite fixed, with 4 out of 11 circles and 7 out of 11 crosses. And so when we plug this into the formula, we get, again, a high entropy of 0.946. So now we have all of the component entropies, so we need to combine them together to get our estimate of information gain. And then to calculate the final cost, we need to calculate the difference in entropy between the parent node and the weighted sum of entropies from the child nodes, which is given from the proportion of samples each child receives from the parent. So in the left branch, we have 12 out of 23 of the examples from the parent with an entropy of 0.65. And for the right branch, we have 11 out of 23 of the parent's examples with entropy of 0.946. And so the total weighted sum is 0.792. So this gives us a final estimation for information gain as the entropy of the parent 0.966 minus the weighted sum from the children 0.792, which returns 0.163. Moving on now to the Gini index. Gini score gives an idea of how good a split is by how mixed the classes are in the two groups created by the split. A perfect separation results in a Gini score of 0, whereas a worst-case split with a 50-50 split of the classes in each group results in a Gini score of 0.5. As before, the final Gini index for the group must be weighted by the proportion of samples in that child relative to the total in the parent. And so the final score is again a weighted sum of the Gini scores for each child node. Going again through the same worked example, but this time for the Gini index. As before, there are 23 instances, 14 circles and 9 crosses in the parent. And in the left child, there are 12 instances with 10 circles and 2 crosses. And in the right node, there are 11 instances with 4 circles and 7 crosses. For the Gini index, we can ignore the parent node and just look at the proportions of the child nodes. So in the left child, we have 10 out of 12 as circles and 2 out of 12 as crosses. We need a sum of squares of these proportions, so this returns 10 over 12 times 10 over 12 plus 2 over 12 times 2 over 12. And then to get the Gini index, which is highlighted at the top here, we must subtract all of this from 1. We then do the same for the right node with 4 out of 11 circles and 7 out of 11 crosses. This gives us a Gini score of 0.463 for the right node and 0.278 for the left node. Then, as before, we combine these as a weighted score to get the final cost. So again, weighting by the proportions of samples from the parent and each child, we get 12 out of 23 for the left node and 11 out of 23 for the right node. Multiply each of these with their individual Gini scores and sum them together to get a final score of 0.366. So we've learned 2 possible cost functions of classification, but which is best? For datasets containing many categorical variables, information gain is biased towards attributes with more categories. Therefore, for scikit-learn, Gini index is default. Note that in order to build a decision tree, which we will do in Tuesday's tutorial, you are going to have to use these learning rules to pick which feature to split on for each node of the tree. And so you will need a notion of which cost is best, which feature performs best. And so you will need to compare these Gini or information gain scores for every feature. Importantly, you have to remember that when using each splitting criteria, the Gini index must be minimized, so you'll look for the feature that has the lowest Gini index. On the other hand, the information gain must be maximized. So if you're using information gain, you are looking for the feature that has the highest information gain. Finally, before we finish this section, let's just quickly touch on what happens with regression. So in regression problems, you are going to be asked to split up your feature space into ranges where you can approximately and locally fit the data. So like before with classification, you might be offered a few choices in terms of how you do this. An algorithm might fit a constant function. Clearly, this is not doing amazingly over large ranges, but as you build up your tree, you're going to chop up the ranges, in other words, the range of the x-axis shown here, into smaller and smaller sections. And as you do so, similarly to what we were seeing with nearest neighbour graphs in the previous video, As we make the approximation more and more local, it will get closer and closer to fitting the data. Some other methods, however, may allow you to use a polynomial fit, so a curve or a line, or even a probabilistic fit. However, for all intents and purposes, you can ignore these because, from what I can tell, scikit-learn only allows you to fit constant functions. So then it comes to how you decide on which feature to use and what constant function to fit. There are many different possible costs that you can use to do this. A popular one is mean squared error. This looks at the distance between each feature and the predicted fit, the constant function y hat k. And as with all decision stumps costs, it will create a final result as a weighted sum across the children of each parent node. So in summary, weak learners are learners that individually do only slightly better than chance. There are several options of increasing complexity, but in this course we will only consider axis-aligned rules for classification and constant functions for regression. A decision stump is both a weak learner and one level of decision tree. And focusing specifically on classification, we use axis-aligned classifiers which seek to fit a threshold on a single feature. This seeks to optimally split the data from each class down different branches and uses either information grain or Gini index to split on. The goal is to reduce the mixing in the children relative to the parent node, and the final score for these costs is estimated as a weighted sum of the contribution from each of the children. In the next lecture, we will see how to stack these decision stumps together to build a decision tree. So before you go on to do that, test your knowledge in the Keats quiz on weak learners and decision stumps.